no questions. So where were we last time? I actually kept the slides of last time here because maybe they form like a nice starting point. What we did last time is that we looked at reflection and transmission in a very simplified circumstance where the electromagnetic wave, which is a pure plane wave, and you visualize the electromagnetic plane wave properly. It's a very strange beast that actually doesn't exist in nature. It's a full plane extending to infinity, has no dependence in these two directions, and it moves in a certain direction like this, right? So it has temporal direction dependence, it has directional dependence in one direction, but the rest is a big plane. Okay, so it's like an infinite plane moving. And now this infinite plane is hitting a boundary between two different media characterized by their own parameters, the permittivity, permeability. The one assumption that is made is that these are linear isotropic media, and therefore, you remember, we could use these simplified equations where essentially these polarization, magnetization fields were proportional to respectively the electric field and the B magnetic field in matter. So that's not always the case. We've made a number of simplifications here. Okay, that was the setup. So we had a certain incoming incident electromagnetic wave. It had a polarization vector, the polarization being the direction of the electric field. And given direction of electric field and propagation direction, you know the direction of the magnetic field, because the pointing vector tells you that E cross B is the direction of propagation. Okay, so that's the way it goes. E cross B propagates this way, hits the boundary, gets reflected partly and transmitted partly. And now the mathematical problem was posed as follows. Again, if you're a mathematician, you think of it in these ways. You've got two half spaces, half infinite spaces, the space with Z less than 0, showing the incident and the reflected wave, and then the space with Z greater than 0, showing the transmitted wave. If you're thinking about the solution of the Maxwell equations here, then you know that in free space, we have already written the solution for these monochromatic plane waves. These were these free waves that we had here. There was a relationship between the B part and the E part coming straight from the Maxwell equations. You remember that the B was essentially K hat cross N or K hat cross E in the other direction. So essentially, you write down this ansatz here that automatically fulfills your Maxwell equations in both half spaces. Then the only challenge remaining is to actually match the boundary conditions on the electromagnetic fields at the interface between the two media. Okay, hopefully this whole logic is absolutely completely clear and almost trivial for you at this stage. Okay, so that's fine. Any hesitation on this, how we did it? Sometimes we kind of went perhaps a tiny bit fast in the derivation of our things, but I hope that it's all okay. So first of all, the fact that everybody's got the same time dependence is of course necessary for these equations to work everywhere. The fact that these identities and these matching conditions are independent of the coordinates on the interfacial plane, namely the xy at z is equal to 0 plane, that allowed us to just really identify the waves left and right without doubting about anything here. Okay. Of course, if I had a much more complicated wave that had different frequencies associated to it, then I would just repeat this very calculation for all the different available frequencies, because by linearity, I know that all these frequencies of the electromagnetic waves are independent of each other. The linear superposition, the addition of all these partial solutions is also a solution. So whatever time dependence you would give me on the incoming wave here, I could also treat with this just by doing a Fourier decomposition in omega of all these components. Okay, so this setup here, although it looks restricted to these particular waves, monochromatic plane waves, it's the solution for whatever wave as a time-dependent thing. It could be even a pulse coming in. You'd be able to compute all these things. Yes. Question.
Do you know the other frequencies share the same P0 or?
No. So essentially, what you would need to do here, if you had an incoming wave which was not monochromatic, which was like plurichromatic, although it's like not quite sure that that's a word in common use, you would give each of these components their own individual amplitudes, because they are really independent of each other. There's no relationship between the amplitude at a certain omega and the amplitude at another omega. Okay, so you would fit the wavefront. Essentially, these E zeros I here would then become the Fourier components of the incoming wave in frequency space. Okay, and then once you know the frequency, then I mean the K vector and the omega vector, they're related to each other, right? So the norm of the K vector, so omega has to be C times K, or V times K, where V is the velocity of light in that particular medium. Okay, that has to be the case because of the wave equation that we had written down, right? So when we did we actually rewrite it? Well, we did it last time. So, but when you obtain the wave equations from this, you remember you just take the curl of this equation here, and then you obtain the equation that tells you that the Laplacian of the field is equal to epsilon 0 mu 0, the second time derivative of the field. Then that equation is fulfilled provided you choose omega is equal to velocity of light times norm of K. Okay, so that's your question.
Why was the reflected B field negative?
Why was the reflected B field negative? Purely by convention of the axes on which we define our things. So here you see there's incident and reflected. And at this point, if my, say, amplitude of the incoming wave is positive in the positive x-axis, since I haven't done my calculation yet, I don't know what my reflected electric field will look like. It will be either pointing up or pointing down, okay? But it doesn't matter that I don't know. I just need to establish the convention that I will use to describe it. And then we say, well, okay, what we're going to do is we're going to call positive reflected electric field going up this way. And then for convenience, we're going to put the B this way, because then if you've got positive E, positive B, then you've got propagation direction like this. Okay, so it's just a choice of axis. You can elect to do that differently. It's a choice of coordinate frame for that particular thing. So it's there's no physics in it. Right? Okay, so so that was that. Then what we did is that we just essentially computed the reflection and transmission coefficients by fulfilling our boundary conditions at this interface between the two regions. And this was essentially just an algebraic exercise. The non-trivial point is, of course, that we have to fulfill our boundary conditions, namely on one side, it's the incident plus the reflected bits that contribute, and on the other side, it's just transmitted bit. That's why we had these linear relationships between these amplitudes, but with coefficients that were given by the boundary conditions that we had written before. And just to remind you, these boundary conditions we had written in general for the case of linear media in these equations here. So the perpendicular component of the magnetic field in particular is continuous. The parallel component of the electric field is continuous. And the rest is essentially set by some potential free charge density or current density at the surface between the two regions. Okay, and again, this came just from the integral form of Maxwell's equations in matter. Okay, so so now what we're going to do today is essentially exactly the same thing, or at least we'll do that a little bit. So what are we going to do now? We're actually going to complicate our setup a tiny bit.
Sir.
Yes. Sure. Yeah, I like this. Yes. Yes.
Well, in the equation that's marked by one star, the equation says that the incident amplitude is lower than the transmitted amplitude. I'm kind of confused by it.
This one here, right?
Yeah.
Yes.
But, how can you have a wave that's coming in that's smaller than the wave you're transmitting?
At this stage, we are not saying that one is smaller than the other because the sign of these e's are not determined. So these are real numbers, yeah?
In the sketch, all the vectors for nothing, so we all have the same.
Yes, however, this is my axis. Yeah, so if the number along this axis was positive, then the field would be positive this way. But if my axis is like this and my value becomes negative, then it's just that my electric field points the other way. So this choice here is a choice of axis rather than a choice of field, because the field comes out of the calculation. But the expression of the field relies on your parameterization of the axis. Okay, so for example, I could have put the axis the other way around. I could have done it the other way around, right? I could have put the electric field down and the magnetic field just pointing towards the positive y direction, right? And then I would still have my pointing vector going away from the boundary. But now in my equation for the electric field, if I did that, I would need to put a minus sign here. Because then a positive value for the incident with a positive value for the reflected in that different thing, they go against each other. Therefore, the value of the field. But now doing these two things together here with the same axis here, that's why I can do a plus here. So it is purely conventional for how you label the field. Okay, so there's really no statement yet about the intensity of any of these fields. It is at this stage only a parameterization that will then give you the physics once you've solved all your equations. But at this stage, nothing is set. Okay, so and to kind of allay your fears, when you do look at the reflected and transmitted intensities that you have here, then you say, yeah, okay, so I mean, fine, yeah, so it kind of looks all right here, because certainly if I look at the physics of it, if I look at the energy flow, the power that goes through the that goes with the waves, so with this intensity here, then these coefficients are manifestly less than 1. Okay, and that so then it's okay. If you were to get a wave that was amplified in its energy content after being reflected, then there would be a problem, because you don't have an energy source on the other side, and then you'd have invented a perpetuum mobile. You'd go straight on Twitter, you'd become world famous, everybody would recognize you, you'd become a billionaire, but you would be utterly wrong. Yeah, which in this day and age doesn't matter anymore, because you can still get rich. But you know, you wouldn't gain the respect of people like me. So that's the thing. Okay. Okay, so yeah, that's what we did with this. Now let's see. So like I said, we're going to massively complicate our problem here, because we're going to now consider at our boundary an incoming wave that has a certain angle, and then there's going to be reflected, and then there's going to be like this. So let me do it like this. Okay, so so what I have here, I'm going to have an incident wave, I'm going to have a reflected wave, and I'm going to have a transmitted wave. And just to be clear, I will put an angle theta incident on this one. Here, this will have a theta reflected, and here there will be a theta transmitted. Okay, sorry for the small thing, but that's the way it would look. The incident wave would come in with a wave vector ki. The outgoing wave would go out with a k reflected, and then this one would have a k transmitted. Okay, so that's what I'd like to have. So this is going to be medium 1, medium 2. And now what we have an immediate way of writing our incident wave. For example, the incident wave is going to be polarized along a certain direction that I'm not going to specify yet. So this is E incident as a function of position R and T. This one is going to have some constant vector here, E0I. And it's going to have just the usual wave dependence, but now I want to keep this slightly more general. So there's Ki dotted into R minus omega T. Now, just from the fact that this is a monochromatic plane wave, I can immediately write the magnetic field associated to it as well, just because from Maxwell's equation straight, as we've seen, the B field is going to be related to the E field by dividing 1 over the velocity. So this is the velocity in the first medium here. And now I will have again just the K vector for the incident wave crossed into the electric field of the incident wave. Okay, so with these electromagnetic fields, I have solved the Maxwell equations as far as this incident wave is concerned. Okay, so that's already a complete solution. Now, for the reflected wave, I'm going to have absolutely exactly the same thing. Okay, so E reflected, B reflected, really the same thing. RT is equal to E now. 0 reflected, e to the I K reflected dot R minus omega T. And B is just 1 over V1 K reflected, sorry, not this one. K half reflected cross E reflected. Okay, so that's one, just the same thing. And for the transmitted wave, well, you'll have guessed it, you know, E transmitted, B transmitted is really the same kind of thing, except that again, I just have to use the K transmitted dot R. And here I need to use the velocity in the second medium. Like this. Okay, so in principle, that gives me all these waves that I have to deal with, both the electric and the magnetic components. So I emphasize we have not yet chosen a direction of polarization for that field here. The only thing that we know, we remember the transversality condition for electromagnetic waves. We know that given the propagation vector Ki, then the polarization of the polarization of the wave, so the direction of this thing, will have to be in a perpendicular direction to that. But we still have a full angle to choose on this that we'll do later. Okay, so that's the first bit. Now, so all waves, yeah, so they are all at frequency omega. Okay, everybody. So we know that to solve the wave equation in free space, we need omega is equal to Vk. Okay, so since omega is equal to V times K, where K now is the modulus of whatever vector we have here, what we have as a condition is that, of course, K incident V1 has to be equal to K reflected V1 is equal to K transmitted V2. Okay, so immediately from this, add ourselves a bit of space. So immediately from this, we have that the K incident is equal to K reflected. Again, these are amplitudes, right? So this is the modulus of the vectors, and this one is just the ratio. So V2 over V1 K transmitted, and we had related. You remember the we had done that. Let's see. Here, yeah, we had introduced this refraction index essentially as the ratio of the velocity in the medium to the velocity of light. Okay, so if I just use that here, this becomes, this ratio of the velocities here becomes just the inverse of the ratio of the refraction indices. So this is now N1 over N2 K transmitted. Okay, so that's the first thing. Okay. So now we need to solve the boundary conditions. Okay, and our boundary conditions told us that, for example, E parallel in 1 has to be equal to E parallel in 2. Okay, so parallel to the plane, right? So here, just to be clear, you know, we can make a choice of our directions. Maybe we're going to use the same conventions that we had before. So what we had before was this. This was the x-axis. The outgoing vector was the y-axis, and this was the z-axis here. Okay, this is really the same choice that we had made before. Okay, so now the parallel components of the electrical field in the plane of the interface, they have to be continuous. And that has to be continuous absolutely everywhere. So anywhere where I put you know, I take the x direction of the field and I put z is equal to 0, these incident plus reflected amplitudes have to be equal to the transmitted ones. Okay, so yeah, we can deduce a few things about this. So first of all, the x component of these vectors has to be you know, just related. So essentially the k incident x component has to be the k reflected x component. There, maybe yeah, maybe we can just write it straight here. You see, what I want to have is that these spatial dependencies here in x and y, when I put z is equal to 0, have to be the same for everybody. So really the condition is that if I have a k vector incident dotted into R, that has to be the same thing as the k reflected dotted into R, and that has to be the same thing as the k transmitted dotted into R when I evaluate this at z is equal to 0. Okay, so that's the kind of first condition. So yeah, so what that means is that the x and the y components of these vectors have to be equal. Okay, I, y. Okay, yes.
So the boundary condition is that the electric field at the plane 1 and the second, like 2 sides, should be equal. Parallel parts. Yeah.
So here, right, this is at z is equal to 0. Yes.
But then why don't we add incidence and reflected to the
here I'm not doing yet the amplitudes. Here I am writing restrictions on the wave vectors that are contained in the waves. Okay, so here see what I'm doing. I'm essentially indeed looking at EI plus ER is equal to ET, but the parallel components, when I evaluate Z is equal to 0. So I'm doing this at Z is equal to 0, plus this at the same point, but Z is equal to 0, has to be equal to this also at Z is equal to 0. But in here, I still have some X and Y, okay? And this equality between these things has to hold irrespective of the X and Y, okay? So in order for that to work, then whatever function of X I have in one has to be the same function of X in the other and the same function of X in the third one. Therefore, the only function of X that I have is, kx times X for both the incident, reflected, and transmitted. So the kx's from this wave and this wave and this wave, they have to take the same value for this to be true for all X. Does that clarify what I mean? And then it's the same thing with the Y. Question?
Question about that formula. I think the same that one that he was asking about this ki dot into r ki dot.
Yeah.
I don't understand why this has to be the case.
Okay, so let's just do this more explicitly. Okay, so what do I get? What do I get from this? What I get from this is that if I take the E incident RT plus the E reflected RT, and I evaluate that thing at Z is equal to 0, that has to be equal to E transmitted of RT evaluated at Z is equal to 0. Okay, but now let's do this explicitly. Let's just write it long form. Okay, so what does that thing imply? It implies that I have my vector E0I, and now I have E to the I, and I've got K incident dotted into R, but Z is equal to 0. Okay, so I'm going to write this as K incident X times X plus K incident Y times Y. Okay, minus omega t, plus now the reflected bit, which is E0 reflected E to the I, K incident, say K reflected X component times X plus K reflected Y component times Y minus omega t. This has to be equal to E transmitted E to the I, K transmitted X component times X plus K transmitted Y component times Y minus omega t. Okay? But this holds for all X and Y, and by orthogonality of the free wave coefficients E to the I, K, X, and whatnot, that means that the only way that this is going to be satisfied for any X and any Y with given vectors like this is if the spatial dependency of each is the same. And therefore, K incident X has to be equal to K reflected X has to be equal to K transmitted X. Okay? And the same thing for Y. Is that abundantly clear? So the reasoning is complete set of independent functions, if you want, or in this case, specific functions here. However, the boundary condition is valid for all positions on the boundary. And given that I have an explicit function here of X, then my only hope of finding a non-trivial solution to this boundary condition here, non-trivial meaning that these constants here, here, and here can be non-zero. Of course, if I put all these constants to 0, then of course I've got a solution. Yeah, but you don't get paid for that. Yeah? Okay. So if these vectors are non-zero, then the only way this boundary condition can hold for all points on the boundary, namely for any value of x and y, is if the wave vectors of the incident, reflected, and transmitted in the plane coincide. Have I clarified your?
I think in the first instance, what I didn't understand is that there are two terms in the beginning, then one at the end. So I would think that KIX plus KRX is KTX, something like that.
Yes, but you see, but these, yeah, sure, fine. However, because it's still valid for any x, it still is the case that these k's for the incident and the reflected have to be the same. The only way you're going to get, say, coefficient 1 times e to the I k1x plus coefficient 2 e to the I k2x is equal to coefficient 3 e to the I k3x for any x. The only way you will fulfill this condition for non-zero C1, C2, C3 is if K1 is equal to K2 is equal to K3. They have to go together the whole time as you change in space. Okay? If, I understand there's an addition here, but it absolutely doesn't matter. Yeah, because if it had a different K here, then there would be X's for which this condition wouldn't be fulfilled. Okay? Is this completely clear? So sometimes, indeed, kind of go fast with these things, but once again, in doubt, always put your feet on the boundary conditions, because the boundary conditions tell you everything that you need in terms of the constraints that you need to put on your general forms. Okay? So that's the first bit that we have here. Okay. So yeah. So you see what that tells us is the so-called first law of reflection. So the incident, reflected, and transmitted waves are in one plane. Okay, so if one has a certain certain x and y component, then so does the other one. If the incident has a certain xy component, then so does the reflected, so does the transmitted, and the only one that can differ then is the z component of the vector. So this is this plane here is just called the plane of incidence. Okay, so that's the first law. Okay. Yeah. So then the other thing that we have. Yeah, so you see now what we can do is view these three waves here as being in the same plane, right? So irrespective of which direction this thing comes in, this one is going to be in the same plane, and this one as well, right? So if I had a surface and I was coming in a certain direction, then the reflected would go in the same plane and the transmitted would go in the same plane as well. Okay, so now what I can do is whatever angle I'm coming in, it doesn't matter because there's that plane like this. So I can kind of rotate my point of view. I mean, I can rotate the whole boundary as I want because it's just a plane like this. So now I can just rotate the boundary so that I'm coming in with an angle which you see fully described by our incident angle like this. Okay, so namely in this case here, we choose our coordinate system such that the wave has no y component. Okay, you all see what I mean? So that's this thing. And now, if I have these things here, then the second thing that I can say is that again, you see the x components have to be equal, right? So that means that if I specialize now this equation here to what I have here, once I've chosen my plane to be the plane of incidence, then that means, so the x component of this one becomes k incident modulus times the sine of this angle. The reflected one is amplitude of k reflected times sine of this angle, and then the sine of this angle here, kt times sine of this angle. So then the other law that I get. So yeah. So putting our axes such that the plane of incidence is equal to the xz plane. Then what I get is that I have the relationship k I x is equal to k r x is equal to k transmitted x. That tells me that ki sine theta I is equal to k reflected sine theta reflected is equal to k transmitted sine theta transmitted. Okay, so theta, so we had, yeah, so since, like we've shown before, ki is equal to kr is equal to n1 over n2 k transmitted. What I get is theta I is equal to theta r. So the reflected angle is equal to the incident angle, and the n1 sine theta incident is equal to n2 sine theta transmitted. Yeah, I got this right. Yeah, so these are the so these are the laws of reflection. And this one is Snell's law. Yeah. So you see these laws of reflection that you learned at school. They really come from the solution of Maxwell's equations, really. Okay, so that's